All right, so here we are for part 4 of section 5.4. In section 5.4, part 4, we're going to take a look at something called the net change theorem. Now, in part 1, I told you that this is, in my opinion, one of the most application-heavy ones. Okay? So, here we go. You ready? The fundamental theorem of calculus states that the integral from a to b of little f of x is equal to big F at b minus big F at a. But if we make just a tiny little change to the integrand, if we rewrite little f as f prime, we still get the same result. That is, we still get f of b minus f of a being the value of the integral. But it allows us to change how we think about things. So if we think of f prime being the rate of change of some quantity, okay, it's measuring how fast something is changing because that's what derivatives do, then what does f of b minus what does f of b minus f of a stand for then? Well, it would be the net or the total change for that quantity on an interval. Now, the most common application, the one you're going to see the most often used here, would be the idea of if f prime represented velocity, then when you integrate velocity, and I'm right here, in case you're wondering where I'm at, when you integrate velocity, you get position and position. And so the integral velocity gives you position at the ending time minus position at the beginning time, and position at the ending time minus position at the beginning time is going to give you how far you displaced that object on that given time interval. Right? Now, one of the challenges that we have with using this net change theorem in this way is the same challenge that we had when we discussed displacement and distance earlier. This was a couple of sections back, that displacement does not equal distance traveled unless the object is only ever moving in one direction. Okay, so if you have an object that is always moving right, then displacement would be the distance that it moved right. If you had an object that was always moving left, then displacement would be the distance that it moved left. But if it ever changes direction, then displacement is not equal to distance. But we can fix that by doing this little bit down here. We say that the displacement on an interval is just the integral, the definite integral of velocity over that time interval, and that total distance traveled on an interval is just the integral of the absolute value of v of t. Now here's the problem, though. Here's the challenge that we have, is there is no way to evaluate an integral that contains an absolute value. So what you would have to do to make this thing work is you have to rewrite it so that it ends up looking something like this. Where the integrands at every step are either v of t or negative v of t, depending on whether your velocity is positive or negative on that interval. Okay? If the velocity is positive on that sub-interval, then we just leave it as v of t, but if the velocity happened to be negative on that sub-interval, we would put an extra negative in there to make it back to positive, and then you just add up all those chunks, and all those chunks will give you your total distance traveled. The true challenge in that is figuring out all those x's that you have to break it up into, because you have to take your velocity function, figure out where it's positive, figure out where it's negative, find all those intervals, and then rewrite it. In fact, that's going to be the example we're going to do. Okay. The velocity measured in feet per second of a particle moving along a line is v of t equals that hot mass, that cubic equation right there, where t is the time measured in seconds. Okay. What is the displacement of the particle on the time interval 1 to 5? And what is the total distance traveled by the particle on the same time interval? Okay. And luckily for us, we have this lovely picture over here to represent the function v of t on that time interval. All right, so first things first. We have two questions here. I'm going to label them 1 and 2. We're going to answer number 1 first. Okay? Since I'm finding the displacement on a given time interval, I am going to, first off, label it so that if I look back at my notes later, I'll know what I'm doing. And I'm just going to copy down the formula. So the formula for displacement said displacement is just simply equal to the definite integral from a to b of v of t dt. Now I said simply, but I don't mean this is simple. I just mean that we don't have to make any modifications or changes. We just do a straight up integration problem. Okay? Replacing for this problem with everything that it needs to be replaced with, that's going to give me the integral from 1 to 5, the time interval, of the function t cubed minus 10t squared plus 29t minus 20 dt. And now it's just a matter of evaluating that integral. All right? 1, 2, 3, 4 terms. The antiderivative of the first term is 1/4 t to the 4th. The antiderivative of the second term is going to be negative 10/3 t cubed. The antiderivative of the third term is going to be 29/2 t squared. The antiderivative of the last term is minus 20t. And then this whole thing has to be evaluated from 1 to 5. Now this is definitely an example where I'm going to make use of that rip it apart business. Okay? So that's going to give me 1/4 times 5 to the 4th minus 1 to the 4th minus 10/3 times 5 cubed minus 1 cubed plus 29/2 times 5 squared minus 1 squared minus 20 times 5 minus 1. Okay, 5 to the 4th, let's see, that's 25 squared, so 25 squared is 625. So 625 minus 1 is 624, so this is going to give me 624 over 4 minus 10/3 times 1, 24. 5 cubed is 125. 125 minus 1 gives me that 124 that's sitting there. Okay, let's plug in because my battery is obviously running low. Plus 29/2 times 24, 25 minus 1, minus 20 times 4. At this point, this is a calculator problem. Okay, so 624 divided by 4 is 156. 124 times 10 over 3 is 1,240 over 3. I don't know why I need a calculator for that. I was hoping 124 divided by 3, but 4 plus 2 plus 1 does not add up to a multiple of 3, so it doesn't. 29 times 12, so plus 348, and 20 times 4 minus 80. So 156 plus 348 minus 80 gives me 424. So 424 minus 1240 over 3. So minus 1240 divided by 3 gives me 10 2/3, or 32/3. And then let's see, if velocity is in feet per second, then the displacement is going to be in feet. And since that's a positive number, it means it was displaced 32/3, 10 2/3 feet to the right. Right? Now here comes the hard one, number 2. Right? Distance. Distance is the integral from a to b of the absolute value of v of t dt. And we can't integrate an absolute value, so what we have to do is we have to rip it apart. Now luckily someone gave us the graph, and so I can see that there's something that happens when t equals 1, there's something important that happens when t equals 4, and again when t equals 5. Right? So if my job is to do the integral from 1 to 5, I need this piece, and I need this piece. But to make this distance traveled, I need this to be positive, and I need this to be positive. Now the yellow piece is positive just because it is above, but the purple piece, blue piece over there, that small piece on the right, to make that positive, I have to do the opposite. Here, you'll see what I mean here in a second. That the integral from 1 to 5 of the absolute value of t cubed minus 10t squared plus 29t minus 20 dt, I need to rewrite this as the integral of 1 to 4 of that function v of t dt plus the integral from 4 to 5 of the opposite of v of t dt, the negative of that integral. That's a lot of work, but we can do it. Okay? So then what's this going to give us? Let's see. This is going to give us, let's see, I've already done the antiderivative. It's sitting right there, so I'm just going to reuse it. It's going to give me 1/4 t cubed minus 10/3, oops, that's 1/4 t to the 4th, minus 10/3 t cubed plus 29/2 t squared minus 20t, evaluated from 1 to 4, so that was this one. And now I'm going to cheat a little bit, and I'm going to take this negative right here, and I'm going to move that out in front and say, okay, just do minus 1/4 t to the 4th minus 10/3 t cubed plus 29/2 t squared minus 20t from 4 to 5. Okay? Whew. A lot of work, but I can make this happen. Okay, just going to dive in and start doing this. So this is going to become 1/4 times 5 to the 4th minus 4 to the 4th minus 10/3 times, wait. Totally screwed up my limits there. This is 4 to the 4th minus 1 to the 4th. 10/3 times 4 cubed minus 1 cubed plus 29/2 times 4 squared minus 1 squared minus 20 times 4 minus 1. Minus, and this minus is that one right there, the quantity. Whew. Now I have to do it again. 1/4 times 5 to the 4th minus 4 to the 4th minus 10/3 times 5 cubed minus 4 cubed plus 29/2 times 5 squared minus 4 squared plus, and I'm running out of space here, I'll say minus 20 times 5 minus 4. Okay, now starting from the left over here, I have 1/4 times, let's see, 4 raised to the 4th is 256 minus 1, so 255, minus 10/3 times 63, plus 29/2 times 15, minus 60. 4 minus 1 is 3. Okay. Minus, and so what I'm going to do here is I am going to put a big set of brackets right here so we don't screw this up. All right, so 5 to the 4th minus 4 to the 4th. Let's see, 5 to the 4th, I just did that up here. That was 625. And so I have 625 minus, oops, minus 256 over 4 minus 10/3 times 125 minus 64. Is that 4 to the 3rd? Yep. Plus 29/2 times 25 minus 16 minus 5 minus 4 is, so minus 20. Okay. these are fourths and these are fourths, so I'm going to put those together. 625 minus 256 gives me 369 plus 255 gives me 624. So I'm going to get 624 over 4, and those are gone and those are gone. Wait. I did something wrong there. 255 minus the quantity, 625 minus 256, negative 114 over 4. Oh man, almost screwed that up. I forgot the negative. Oops. Okay, now I'll do my thirds. These are thirds and these are thirds. Okay, I've got a negative 630 thirds from that first one right here, plus, because this minus, this subtraction, and this subtraction are going to make this positive, I need to have 10 times 125 minus 64. So minus 20 thirds when it's all said and done. Okay, so that one's gone and that one's gone. Now I got halves. 25 less 16 is 9. So I have 15 minus 9, that's 6. So 6 times 29 gives me 174 halves. Okay? Does that make sense? 29 times 15, just checking my math here, minus 29 times 9. Yeah, 174. Okay, so this is gone and that's gone. And then negative 60 and a positive 40, so negative 40. So negative 60 and a positive 20, negative 40. Okay, so now I need to add all this mess up. So negative 114 over 4 minus 20 over 3 plus 174 over 2. I know that simplifies, I just don't want to do it. Minus 40. I get 11.83 repeating as a fraction. 71/6, and so this is going to be 71/6 feet is our total distance traveled. Now, I'm going to show you something that you may or may not know already. Okay, the calculator is your friend. I'm going to go up here to Y editor. I'm going to clear out some of this junk that is sitting in here, and in Y1 I'm going to put our original velocity function. I'm writing it as x's instead of t's because the calculator doesn't like those. So x cubed minus 10x squared plus 29x minus 20. And then I'm going to come over here and I'm going to perform a calculation, which is an integral. Wait. Way to do that. Okay, give me a minute. I'm performing an integral. I perform the integral from 1 to 5 of that function y1 dx. 10.66, or as a fraction, 32 thirds, which is this answer right here, because I did this on my calculator. Okay? Let's see if we can get this answer by doing this on the calculator, the absolute value. So again, you can get there two ways. You can use an alpha shortcut, so alpha f2 option 4, the integral from 1 to 5 of, now I need absolute value. So alpha shortcut, absolute value is option 1, of alpha shortcut y1 dx. And then if this works out, we should get 11.83. Or, if you prefer a fraction, 71/6, which is our answer right down here. Now, I am not advocating that you do not need to know all of this, how to do these things by hand, especially if you are going on to Calc 2 or Calc 3 and beyond. You will definitely need to know how to do this by hand because the calculator can only do some of this. Single variable stuff, can't do multivariable stuff that you'll need to know how to do by hand there. But it's an excellent tool for checking your work or to figure something out if it's going to be ugly. I mean, honestly, I had no desire to do any of this by hand down here. If this was a problem that I had been assigned, well, I would have just done it on my calculator and got the answer that way. I know I can do it by hand. I just don't want to. It's tedious. Right? So just so you know, there is a way to do these things on the calculator. All right, so let's take a look at another problem. We're already at 21 minutes, but this is the last problem, so I don't want to make a video just for this. Okay. All right, so here we go. Let's get this last one done. Liquid flows into a storage tank at a rate of R of t equals 180 plus 3t. So let's highlight that. Liters per minute, where t is measured in minutes and t is between 0 and 60. Find the amount of the chemical that flows into the tank during these first 20 minutes. All right, this function, R of t, is a rate of change. And since that is a rate of change, we can use the net change theorem that says that the integral of the rate of change is equal to the total change to make this thing work. All right, so if we take a quick look at what's going on here, 180 plus 3t is a linear function with a y-intercept, or in this case an r-intercept of 180. And they want us to define the amount of chemical that goes in between time t equals 0 and t equals 20. Okay? So we're finding that piece right there. Okay? So then the total amount of liquid that's going to flow into this total amount of liquid that's going to flow into this tank is going to be the integral from 0 to 20 of our R of t dt. Okay? And about the only place that you can make a mistake here is if the units don't match up. And so my units are liters per minute for my rate of change, and my time is being measured in minutes. Now, if my rate of change was liters per hour, if R of t was liters per hour, then I'd have to make a time change and say, instead of 0 to 20, it would have to be 0 to a third, because 20 minutes is a third of an hour. I'd have to make those units match. Okay? But don't have to worry about that here, so this is a pretty straightforward problem. I need to do the integral from 0 to 20 of 180 plus 3t dt. Right? Antiderivative of 180 is 180t. Antiderivative of 3t is going to be 3/2 t squared. And this whole thing needs to be evaluated from 0 to 20. Have I mentioned how much I love polynomials when the lower limit is 0? Because essentially that means all I have to do is evaluate at the upper limit. Because the lower limit is going to zero out for everything. 2 times 18 is 36 with 2 zeros on the end of it. 20 squared, but if I divide by 2, that's 20 times 10, that's 200. 200 times 3 is 600. Why did I write 300? I don't know. 200 times 3 is 600. 3,600 plus 600 is 4,200. And what are these things? Well, this was liters per minute. So the vertical is liters per minute. The horizontal is minutes. And so when you multiply liters per minute times minute, you get liters. So then the answer to the question is, during the first 20 minutes, 4,200 liters flow into the tank. And there we've got our, what is this? Oh yeah, this is the rate of change problem, our second example for rate of change. This brings us to the end of section 5.4. Next video will be section 5.5.